us a set of 3 lectures on very special round of applause because he was supposed to get here yesterday afternoon and was stuck at SFO until early morning hours. He just got here at 5 a.m. and he's still lecturing.
So that's my built-in excuse for complete incoherence. So first, I need to respond to Senthil's talk. Those 3 posters were made by my wife.
Oh, fantastic.
And they're part of a large set which were designed, well, in another era to help with attracting and retaining women to science, something that's presumably now illegal. If anybody wants to, there's a large set, they're very beautiful, so you can contact my wife. All right, good. So what I'm going to do is I'm going to talk about the physics of cuprate high-temperature superconductors. One might ask why. And, well, okay, maybe it's because, you know, for some of us, it's a disease, and I've been obsessed with them for longer than almost any of you have been alive. But there are, I think, several more serious reasons. One is these are, without doubt, the best characterized, experimentally that is, highly correlated material, maybe next to silicon, the best characterized material there is. And so we really have a large amount of rather detailed and, importantly, reproducible material. What people say about the experimental facts change with time as new ideas come. But actually, the experimental facts even have remained remarkable over time. We've added more and more depth and detail of understanding. And so that makes it a very good laboratory for testing our understanding of the theory of correlated materials. Now, you know, it also has a downside, which is that much of what we observe may not be essential to the essential problems. That is to say, much of it may be not seeing the forest for the trees. Now, you know, we all like trees. Trees are beautiful, and all these details that we study are interesting and worthy of studying in their own right, but it also can sometimes obscure observations of what are the essential features. I remember one point when density waves had just been discovered in the cuprates, and I was having a conversation with a bunch of the leaders of the field. I was very excited about this and said that people should go out and look for these charge and spin density waves, this stripe order in other materials. And Phil Anderson said, no, they really shouldn't do that. And his explanation of why they shouldn't do it was that, well, if they look for it, they'll find it. The point is not silly. The point is that, in his opinion, this was a side issue, not related to the central physics of the cuprates, and that once people discover it, they'll become interested in it, and a lot of study will go into this, and this will distract people from the main of cuprate physics. You know, it's a little bit an arrogant position until we know what the central story is. It's a little bit dangerous. What?
Phil was known for his humility.
Yes, he was known for his humility, exactly. But you know, I think it's still not clear whether this is an important central feature or just an interesting side detail in the problem. Actually, although I spent a lot of time studying these density waves are probably going to play very little role in my lecture, although I'm not completely prepared, and I hope I will be derailed from what I intend to do by lots of questions and comments. So the other sort of high-level thing I wanted to say is the following. I never know exactly what top-down and bottom-up means. I mean, usually when we use this, we're resenting the administration's top-down approach, and we want a bottom-up approach, which means something that's generated by us rather than them. But in the theory of emergent phenomena, I sort of think of top-down as coming from high-energy physics or microscopic physics, trying to understand on the basis of fundamental interactions between the fundamental constituent particles what sorts of properties could emerge, and then looking around for experiments that maybe see some of the things that come out of this analysis. A bottom-up approach means looking directly at the phenomena and trying to work backwards to ask what are the interesting theoretical approaches and ideas that could shed light on the observed phenomena. And so what I'm going to do in this lecture, I mean, it's going to be a theory lecture, but it's going to be bottom-up. I'm going to start each discussion with some experimental observations and what that tells us about what's needed on a theoretical grounds. Okay, so that's it for philosophy. So there's a phase diagram, and I also like equilibrium statistical mechanics, and so I start from the idea that the most important thing to understand are the phases of matter, and regimes of behavior are something to graft on top of that. And the important feature of the cuprate high temperature superconductors is the famous superconducting dome. And so we know there's such a dome. It's seen in many families of cuprate materials. The superconducting phase is unconventional. It's morally D-wave, although in some materials, which are, for instance, orthorhombic, there isn't, strictly speaking, a symmetry distinction, but in the sense of what's going on in some ideal phase diagram of the cuprates, this should be thought of as a D-wave superconducting phase. And then, so one thing that's special about this superconducting state that's different from previous studied superconductors is that it's D-wave. And so that's certainly was at the time new, that's old hat now, but that's something that distinguishes the cuprates from other superconductors. So there was else in terms of broad brush behaviors that was noted by many people, but I think articulated the way I'm going to describe it by Vic me, which is that you could take a perspective on Tc, asking not how do we go from the normal state into the superconducting state, what instabilities of the normal state give rise to superconductivity, but rather start with zero temperature data and ask, as you raise temperature, what classes of fluctuations cause you to lose the superconducting order? And there are two numbers that you can in principle measure. One I'll call T sub delta, which is maybe the maximum of delta, maximum of the superconducting gap maximized over points on the Fermi surface. And just because in BCS theory something like this comes out, there's a number in front of that of order 1, but for most circumstances, if you do BCS mean field theory, that number comes out to be approximately half. So I'll define a temperature scale like this. This is a temperature scale set by the gap. The gap is telling us something about how strongly pairs of electrons are bound to form bonds. And so these thermal fluctuations tell us about at what temperature scale the bosons fall apart. And then there is another temperature scale, which can be written like this. It's kappa 3d times some length, or in a quasi two-dimensional system, this is kappa 2d, the stiffness in plane, which corresponds to L equals the lattice constant in the c direction. And what is kappa? Kappa is the coefficient in the low energy description of the collective modes. Sorry. Of a superconductor. Kappa is the superfluid stiffness. And in 2D in particular, you can see it's of energy. And so kappa characterizes the temperature scale at which phase fluctuations, collective fluctuations of the order parameter, would be expected to destroy long-range phase coherence. In usual superconductors, this scale is very large. Let me just do some dimensional analysis to give you an idea. So I'm here using zero temperature data to predict Tc. So in this case, kappa is the zero temperature stiffness. Of course, kappa is temperature dependent. It must vanish at Tc. But here I'm looking at zero. So let me stick to 2 dimensions. So kappa 2d, I can think of this as being h bar squared over twice. Now, I'm going to be, I don't know. It's easier to put in everything I'm doing is really dimensional analysis, so I shouldn't be taking number 1 seriously, but just for fun, I'm going to. So the mass of the boson, I'm going to write as twice the mass of the electron because it's a Cooper pair. And the density of bosons, I'm going to write as a half the density of electrons because, sorry, I want to do this in 3D. The conventional superconductors are 3D. So T theta is equal to this. This is from the 3-dimensional density. And then the length scale is the length scale of the shortest allowed length scale for phase fluctuations, which should be something like the superconducting coherence length. So if I compute what T theta is for, say, lead or some typical metal with a mass that's on the order of the electron mass, a density that's maybe 10 to the 22nd per centimeter cubed, a coherence length that's maybe 1,000 angstroms, this comes out to be 10 to the 5th Kelvin. Okay, so it means that phase fluctuations play no role whatsoever in Tc. The BCS mean field prescription that the moment bosons form, they condense is well justified. Yeah? So for a clean superconductor, use the full bonds. In a dirty superconductor, this will be reduced by a factor, the fraction of the boson of the electrons that condense, which is a fraction that's L over Xi naught. So if L is 10 angstroms and Xi naught is 1,000 angstroms, that's a factor of 100. That's still 10 to the third Kelvin. So, you know, you're just so far off in these numbers that there's no way in conventional superconductor to make T theta matter. I'm also going to often assume that I'm not in an extreme dirty limit because I'm going to be dealing with a D-wave superconductor. And so at most, the mean free path can be on the order of the coherence length. But okay, ask me if I make that assumption too often. Yes? Nothing. Because long before I reach that temperature, so this would be what the temperature, what Tc would be if the bosons had infinite integrity, if the binding energy of the electrons, rather than being the smallest energy scale in the problem, were the largest energy scale in the problem. So this is an upper bound on Tc. This is the temperature, roughly. This is the temperature beyond which only phase fluctuations would be sufficient to destroy superconductivity. But because it's so many orders of magnitude bigger than Tc, you know that this makes no difference in conventional superconductors. Okay? Now, in the cuprates, on the other hand, first place, they're quasi-two-dimensional. They're layered. The c-axis coherence length is less than or of order the layer distance between copper oxide planes. So this distance scale here, rather than being a coherence length, is the distance between copper oxygen planes. Each plane more or less behaves like its own phase stiffness reservoir. And the electron density in the cuprate is rather lower than in conventional metals. The lattice constant in the c direction is maybe 6 or 10 angstroms. The lattice constant in plane is something like 4 angstroms. There's only one electron per unit cell. So if I directly use the density of electrons in the partially filled copper band, I get so cuprate, I'm going to get, let's call this N bar. N bar is density of electrons per copper. Let's keep that for a minute. We have mass of the electron over the mass of the quasi-particle, and then we have a number which is 700 Kelvin. Okay, so Tc is 100 Kelvin. So without any interesting physics, just looking at the density of the electron, we're in the range where T theta is comparable to Tc. There are all sorts of things that may change this estimate by making it smaller. For instance, many say masses or like 2 or 3 electron masses than like 1. That would reduce this estimate by a factor of 2 or 3. there's also a question about whether I should be looking at 1 plus p or p electrons per copper. That could also make a up to an order of magnitude difference in this estimate. So this is sort of the biggest number I can get for T theta, and it's already in the ballpark of Tc. Yeah. Exactly. Sorry, I mean, yeah, it's you know, there are numbers, the Fermi energy and the cuprates. I mean, it depends on exactly how you extract it from experiment, but yeah. So, you know, in lead, the Fermi energy is 10 eV, and the cuprates, the Fermi energy is maybe half an eV. So there's already there more than an order of magnitude. No, so it's, well, yeah, it comes, so the length scale here is the c-axis coherence length. So one factor comes from the fact that the length scale that comes in is also an atomic length scale, so that's the other big factor. Yeah. Okay. So, well, okay, you can also measure this quantity. And if you measure this quantity for optimally doped cuprates, you get a number that's very close to being equal to Tc. So Vic and I abstracted from, and we drew a sketch like this. We said, look, probably the superfluid density has got to vanish as you approach the insulating phase. So we said, probably we should be drawing a form like this for T theta. And there was data here in the underdoped side that showed that both Tc was equal to T theta and that Tc varied in the same way. And on the other hand, there was already some data that suggested that pairing maybe was stronger as you approached near the antiferromagnetic insulator and dropped as you get farther away from the antiferromagnet. So we drew a sketch like this.
When you say pairing is stronger, that's the pseudo gap that you're referring to, or?
So, no. So remember what the strategy here is. We're using zero temperature data to predict Tc. So this is a measurement of the gap at zero temperature. Now, it's supposed to be a measure of the superconducting gap at zero temperature. And at the time, there were gaps, but we, of course, didn't know how to distinguish the measured gaps from the superconducting gaps. So fortunately, we do now. So there are a lot of things about this sketch that were right. So I think there's now no doubt that phase fluctuations are important for the cuprates. So for instance, there's data on very clean, optimally doped materials that show very cleanly within 10% of Tc that you see 3D XY behavior. This has been seen by Bon and Hardy in the temperature dependence of the superfluid density below Tc, and it's been seen by Meingast in really brilliant experiments on the thermal expansivity, which is expected to have the same critical behavior as the specific heat. In fact, I think that data may have the largest range of reduced temperatures in which critical scaling is seen of any critical point in a solid. You know, solids are shit for critical. This is as good as any. Any critical. Yeah. You know, you always have disorder and inhomogeneities and strains. It's very hard to get very close into TC. Yeah, yeah. I think they rarely go for more than 1 decade of reduced temperature, and this goes for 2. Good. So I'm going to spend a little time talking about what sort of these things represent, inspire. There's all sorts of things respect couldn't possibly be right. So it has the advantage of being very simple. Actually, maybe I have room here. Let me draw what. Now, one of the things when you sketch phase diagrams of the cuprates, there are lots of different families of cuprates. They all have actually rather large differences in their local solid state chemistry. So, you know, at the microscopic level, they're really different problems, and they have behaviors that can be different and depend upon specifics. And so whenever somebody does what I'm doing here and sketches for you some sort of composite phase diagram, to some extent they're lying to you. We're, you know, picking and choosing which aspects I like best and which aspects I think are, you know, specific details associated with one particular cuprate. So just be warned about that. You can ask me if I'm violating your favorite family member. Yeah, I think he was first.
Sorry, before you go on, could you say again exactly what being able to see many decades of 3dxy behavior near the phase transition means? So isn't that just because of a short coherence?
So this is interesting. I mean, you know, usually you would say it's because you would estimate the Ginzburg parameter. If you estimate the Ginzburg parameter, actually, it's quite small, even in the cuprates. So this was something that really upset people who were experts in superconductivity because, you know, the Ginzburg parameter comes out to be, I can't remember, a 30th or something like that. So you would have expected rather small fluctuation regimes. So I think this small phase stiffness is actually a distinct parameter. But, you know, this is, I mean, you know, it looks like the 3D XY model in over the range. Or, you know, okay, so maybe a 30th isn't so far from a 10th, you know, maybe it's just a question of numbers, but at least it's not obvious. But this small phase stiffness is obvious. That's directly measured. I'll talk about the Ginzburg parameter later, so let me put that off.
Yeah, so I think there's a very interesting point in that sketch of d theta. You know, well, one could have said, look, that's just Morton's later. But on the other hand, there's a failure mode for that sketch, yeah, where the Morton Slater is separated by a strong first order.
Yeah. So I will get to that. There's all sorts of things that are stupid here. To begin with, I told you this was zero temperature data, but there's no way you're measuring the zero temperature superfluid stiffness in a non-superconducting sample. And so, you know, we were sort of confabulating, various theoretical ideas and various experimental ideas. We said, you know, probably disorders playing a role here and probably quantum fluctuations are playing a role here. Certainly antiferromagnetism. In fact, Vic and I had been arguing that the transition from the antiferromagnetic insulator must generically be first order. So there are lots of problems with this picture over here. There's also a clear problem with the picture over here, which Senthil mentioned in his talk, although he didn't know he was talking about this, which is that if this is describable by BCS theory with the gap vanishing, then this can't come down linearly. It must have an essential singularity. It must be curved. So there are all sorts of, you know, internally inconsistent aspects of what we drew, and there are also ways it disagreed even then with experiment. So let me sketch now more of what is really seen. Unless there are more questions. Yeah. Okay. Yeah. Yes, good question. So they're 2D-like in the sense that they have a big resistance anisotropy. The electrons move much more easily in 2 dimensions than in 3 dimensions. And so many properties, certainly if I'm thinking about the mechanism of superconductivity, I'm perfectly happy to think about 2D models. But when you study critical phenomena, the rules of the game are a little bit different. And so if I have a 2D, a layered system with weak interplane coupling, it very, very rapidly crosses over to 3D critical behavior. So even with enormous anisotropy, you would expect to see over most ranges critical behavior. And these best data are actually on YBCO, which also turns out to be the most, I mean, it only has a resistance anisotropy of 100 or something like that. So it's still rather two-dimensional, but much less. Okay, but I'm glad you caught that. That's an important point. It, you know, depends what hat you put on, whether you want to treat these as two-dimensional or three-dimensional. Any other, yes? Yes. So what is the question?
You think that it would compare to those more conventional 2D systems?
So, you know, I think to give a detailed answer will take too long. You know, one thing is 1D is not a great place for superconductivity. First place, disorder is really a serious problem, much even than in 2D. And there also are competing density wave orders, which are indeed a part of the 2D physics of the cuprates, but are much, much worse in 1 dimension. So there are some 1D cuprates. There are even some that under some special circumstances are superconducting, but they're hard to deal with, and there's not nearly as much known about them as about the cuprates that I'm talking about. Any other questions? Yeah. What's what?
Cuprate, what is delta by Tc ratio?
Right. So I'm about to get to truth now. So, all right. So first place, we had this part right. Okay, you know, of course we had this part right. It turns out we had this part pretty much right also. So in order to sketch that, I have to tell you how do we sketch this. And so this is not a thermodynamic quantity. So it has to be now spectroscopically. And one of the problems is that gaps don't come with a label that tells you this is a superconducting gap, and this is a charge density wave gap, and this is a pseudo gap, and this is a density wave gap. So you have to have a way, if you see a gap, to identify it. Now, in a usual BCS superconductor, this isn't a problem. There is a gap that's 0 above Tc and opens in some order parameter as you go below Tc. So there's no ambiguity that this is a superconducting gap. But in the cuprates, the spectroscopy is very much more complicated, especially in the underdoped regime. There is a pseudo gap, but in the overdoped regime, there's also evidences of gaps that persist above Tc. So one thing one can do is to look at the gap in angle-resolved photoemission. Now, that has two problems. One is it can only be done with really high precision in the Bisco family of cuprates, because these are the only ones that have the really nice surfaces that allow you to do this sort of high precision ARPIS. The surface probe. And so you can always ask yourself whether being is characteristic of all being, even in Bisco, is special to the surface. I think there are very reasons to think these aren't serious. I'm not going to worry about them. But, you know, since I'm young and impressionable, I'm trying to be realistically honest. So the advantage of this is you can look at the gap near the node. And so superconductors have a nodal gap right at the Fermi energy, and nothing else sensible does. So I think there's every reason to believe that the gap you see opening up on the Fermi surface in the neighborhood of the node is the superconducting gap without any ambiguity. And then one can turn that into a number, say, fit that to a cosine kx minus cosine ky form and ask what its amplitude is. And you can plot that amplitude as a function of doping. And if you do that, unfortunately, there are some differences in exactly what number people extract. And I don't think it's actually due to differences in data. I think it's differences in data analysis. But no matter how you do it, you come out with qualitatively the same thing, which is that you have something that goes like this. And so over here, T delta, first place, has qualitatively different behavior than Tc does. And it can be 3 or 4 times Tc. So, you know, it's not like T theta in lead being, 5 orders of magnitude bigger than Tc, but the combination of it being too big and having the wrong qualitative behavior supports the notion that it is not the pairing, but something else that determines Tc. Okay, so no, not the pseudo gap. Again, this is using 0 temperature data or low temperature data, looking at the slope of the gap right near the node, deep in the superconducting state. Okay, so that I don't have to worry about people telling me that it's the pseudo gap and that the gap is something other than superconductivity. Yeah.
Non-sensible that has a D-wave gap form?
Well, I mean, semi-metals have a nodal gap, but you have to fine-tune to get the chemical potential to be at the nodal point. In generic circumstances, the node is either above or below the Fermi surface. So in in a D-wave superconductor, the node is tuned to the Fermi energy. Okay, so that's very special about superconductivity. Yeah.
So when P is large, Tc and T delta are the same, right?
Yes.
Yeah, and as you lower down the doping, it kind of deviates.
I mean, by the same, they're comparable and they move in the same direction.
So,
So now let's say, what does T theta do? So T theta, well, first place, it's 0 here. You know, we could have known that. But T theta does something a little bit strange. It does something like this. So there are a number of things here. First place is T theta always follows Tc, both in the overdoped and the underdoped regime. Now, this was actually known when Vic and I wrote our paper in 1995. It was called the boomerang effect. That the superfluid stiffness rises through roughly optimal doping and then drops again as you overdope. So that was the boomerang effect. We commented on it, but we said, you know, in those days, the overdoped materials were not under very good control. We said this was probably due to bad samples. Now, there's been lots of data. There's been, in particular, amazing data on films of LSCO. Peter was involved with some of these. And, you know, these are really clean films. They're really, you know, well characterized. And, you know, the similar things seen in single layer thallium material. So, you know, this is really a fact. So, yeah.
Sorry, I missed. How do you measure T theta independent?
Superfluid stiffness, it's kappa. So kappa is measured by measuring the London penetration depth or the missing spectral weight from some rules as you go into the superconducting state.
So how can it be low Tc? Like how can it vanish and still have connectivity?
Yeah, so how I just argued that this was a upper bound to Tc. It's a little embarrassing that I've showed it going below Tc. That's what you were worrying about. Yeah, okay, that's a reasonable thing to worry about. I did, but it doesn't. Okay, this is, you know, I'm talking about facts right now. What is it? Inconvenient truths.
But also in the earlier, in your proposal of Vic.
Yeah.
What?
In here? Here. Oh, yeah. So, you know, I mean, there's over here, there's antiferromagnetism, and here there's spin glass, and, you know, there's stripes.
The latest, but in your with Vic, that the first diagram. What did you think about that phase? Is there like a,
You know,
you have a stiffness, superconductive stiffness,
Eh,
you don't have order.
we,
It's almost-
no, it was stupid. What can I say? It's the simplest sketch, you know, what I would claim, I'm going to make another plot, which is what I think we should have said. So since you're pushing me, let me tell you what I think we should have said. What we should have said, so this is going to be the end of my talks, but let me, you know, since you push me. So on this board are experimental facts. I'm very keen on experimental facts. I like to understand experimental facts. But also as a theorist, I think asking the question, what would the problem look like in the absence of disorder, is a reasonable question to ask. And I want to make one thing clear. I talked about having dismissed some results as possibly being bad samples. What I'm talking about now is not bad samples, but that almost all the cuprates are non-stoichiometric materials. They're solid state solutions, which means that there is intrinsic randomness in them. So even if they are perfect, what perfect means that the distribution of strontiums on the lanthanum sites is statistically uniform. It does not mean that it's uniform. And so intrinsic disorder, and for reasons that I'm going to get to, I think that a lot of the things that are perplexing, some fraction of the things that are perplexing about the phase diagram are actually reflections of this, the presence of this disorder. Okay, there are in principle ways experiments without varying doping, without varying geometry. But as Senthil said, I'm a theorist, so you can't stop me from imagining it. So that's what I'm going to do for now. Okay, so first place, my superconducting phase diagram is going to look like this. I'm going to have other so here I'm going to have some sort of superconductor to insulator transition. The arguments that Senthil was making don't apply to a superconductor to insulator transition. I'm not going to take a position for now on whether that transition is first order or second order. And I'm not going to take a position for now on what occurs here, other than that this is some sort of insulator, probably with all sorts of density wave orders as well. And here's superconductivity. Oh, and let me make this clearer. So this is going to come out in some way like this. Okay, so this is a superconductor to metal transition, and so I think that has to come like this. And then I'm going to draw T delta, which is going to come like this. And you're not going to insist that that has to end at the end of the superconducting dome. That's just some spectroscopic feature. Maybe it does and maybe it doesn't. I'm not going to take an opinion on that. And I'm going to have the superfluid stiffness, which I'm now not going to draw past the edge of the superconducting region, is going to rise like this and be big here. Okay, so that's a sketch. That's the idea that I have in mind. You know, this isn't, there's no experiment. Deal. I'll, as time permits, which it may or may not, I'll tell you some things that have given me some encouragement in this, but this at least makes theoretical sense. Yes? So there are several things. One is that the superfluid density continues to rise on the overdoped side rather than plummeting. The first one, yes. So it ends on this side, and this superconducting phase boundary ends in an essential singularity. And I've put another phase here to end the superconducting portion of the phase diagram.
T theta doesn't go below Tc now?
And T theta doesn't go below Tc now. Yes.
So, what's happening with T delta and T theta? But that's where it deviates from, right? Both the fluctuations.
Right. So, yeah, indeed, I meant to say that. That was another. So, another consequence of this picture, an important consequence, is optimal doping is not associated with anything. It's not associated with a quantum critical point. It's associated with the crossover between a low doping regime where Tc is low because the superfluid stiffness is too low, the high doping regime where Tc is low because the pairing scale is low. And so optimal doping in this sketch appears as a cross region. So in this region out here, I should be able to understand superconductivity based on BCS theory, looking at this picture. In this region, I need something totally different. There's only one superconducting phase here. So my colleague Bob Laughlin says that this is not allowed. If there's only one superconducting phase, then I should be able to describe it in a unified treatment over here and over here. I disagree with that. I think that crossovers are every bit as important as phase transitions. And while this is the same phase here and here, the description of that only means they're adiabatically connectable. It doesn't mean that a sensible description is the same of both. I can elaborate on that if that's not clear. Yeah?
Looking at that, the picture above, where you said it's been known for a long time, even in thallium, that the T theta tracks Tc.
Drops back down.
It's clean. Now that transition can't be standard BCS-like because there are lots of uncondensed.
Sorry, this transition can't be clean.
Right.
Here, this is ideal cuprate with no disorder.
Right. So I was going to ask more on what it means to be clean.
Yeah, no disorder.
No. You said.
So here, I'm imagining a perfect crystalline lattice with no disorder. So how I think I go from this to that, that's the next 5 lectures. The number of order 1, Yeah.
Okay. Isn't the thing, like T delta and T theta are sort of like competing? Like,
So there's certainly a broad theoretical reason for this. So on the one hand, we sort of think that, and we're wearing different hats when we say these things, but wearing one hat, we say, yeah, we sort of think that pairing is mediated by some sort of short-range antiferromagnetic fluctuations. And as you move farther away from the antiferromagnet, the degree of antiferromagnetic correlations is decreasing, and so the pairing scale is decreasing. And on the other hand, although maybe there's even a first-order transition here, so I'm again not on all that great grounds, but nonetheless, as we come here, we're somehow approaching a mod insulator, and so the density of mobile carriers should be dropping. Since Debanjan asked this, there is a big difference about uncondensed carriers here. If you measure the Drude weight, so you integrate the optical conductivity over some reasonable range of frequencies, and you ask, how does it vary as we move across here? It varies more or less the same way as the superfluid density does. I can't remember, there's some number like roughly a third of the Drude weight condenses into the superconducting condensate, but it's more or less the amount of Drude weight is increasing here as we sketched here. On this side, the Drude weight is not decreasing. If anything, it's increasing. And what's happening is the fraction of the Drude weight that's condensing into the superconducting condensate is dropping as we go on this side. So on this side, what's happening is we're getting more and more uncondensed carrier, a larger and larger fraction of uncondensed carriers at low energy. This is great because, you know, I didn't have to prepare too many talks. And so, you know, the slower we go, the better. Phase boundary. Superconductivity is one of the few, you know, we talk about phase transitions, but usually, you know, like charge density waves, they're only sort of approximately phase transitions. But superconductivity, this is a real honest to goodness phase transition. All of these are really phase transitions. So this phase is one phase, and the critical line, unless it becomes first order, is going to be the same critical line everywhere. Yeah.
So when you write ideal stoichiometric step,
Yeah.
naively, one would imagine it to have done T theta is going up, Tc is coming down. As you said in the experiments, T theta is tracking Tc.
Yeah.
So you have to attribute that behavior to non-ideality in some way.
Yes.
So the disorders to speak.
Yes. Yes.
So do you have a story?
Yes. So I will tell 2/3 of that story. The important 1/3 that has to do with the strange metal behavior seen over here will be told in Noga's poster. Noga, there. Okay? Any other questions? Okay. Let's see. Crossovers. Everybody's happy with my statement that you can have crossovers and you need different ways of describing things? Okay, good. So where am I? Right. Okay, good. So what I'm going to start with is talking about the theory of this region. So, sorry, let me sort of divide the phase diagram, my ideal phase diagram, into 3 regions. Over here, I'm sort of in a BCS regime where T delta determines Tc. I'm also going to imagine other things like that if we destroy superconductivity over here, we must be in a Fermi liquid. And there's all sorts of experimental evidence that that's wrong. So, you know, beware. I'm telling you things that are counterfactual. Over here, I don't know what it is, but it's certainly not a Fermi liquid. And I'll spend a lot of time explaining to you why it's not any of the easy things that one might imagine. And the only live possibilities for over here is either it's exotic, it reflects somehow physics of a nearby spin liquid, or it's strong disorder effects. And I am not going to sort that out because I haven't sorted it out. And then this is a crossover region, which I'm not going to try to describe at all. Yes?
Specifically projection, the
phase diagram the square lattice Hubbard model, or do you have in mind a different idealized model?
No. So the square lattice Hubbard model is not a model of the cuprates. Square lattice Hubbard model is a beautiful model of highly correlated electronic systems. I've spent as much time studying the Hubbard model as I have the cuprates. I am quite sure its phase diagram looks nothing like this. I'm thinking, for instance, of YBCO with whatever the couplings are in. So I'm doing physics. So I'm
Gating experiment.
what?
Gating.
Heinrich Schon's gating experiment would be good. Yeah. But Peter, there is, there's 5 years ago, there's the demonstration that you could, with pressure, take YBCO oxygen 7 and tune it through the whole phase diagram. This was done by the Cambridge group. The only thing they have is Tc versus pressure. This is a stoichiometric compound. There's experimental evidence that it's much, much cleaner than anything else. The NQR line width is more than an order of magnitude narrower than in anything else. And this possibility has been dangling around for 5 years, and nobody has measured the superfluid density or killed superconductivity with a field and see if it has a strange metal. It's in my opinion, the most important open experiment in the field. Yes?
Pairing symmetry is still D-weight now.
There are no phase transitions across those lines. So there are in my conjectural phase diagram, this is a weakly coupled metal. This is some strongly correlated system. You need totally different theoretical frameworks for understanding them. And we should look at them separately.
You mentioned the Cambridge experiments that they measured.
So you don't know what the doping is. If you plot Tc versus pressure, it looks like this. But translating pressure into doping requires other experiments. Yeah.
So you said what you were saying? I would someone
Be a little bit careful about that. So even in the underdoped materials, when conductivity is suppressed with high fields, they see quantum oscillations, and the quantum oscillations obey Lifshitz-Lifshitz. So even there, at the end of the day, Fermi liquid, the last laugh.
Well,
But
did I mishear you?
yeah, but there are, so what I'm going to be focusing on, now that I've scribbled all over this, you can't see anything, I'm going to try to focus on how can you get a theory in which T delta is large compared to Tc and T theta is comparable to Tc. So that's something that is, as I'll show you, extremely hard from any Fermi liquid perspective. So this observation calls for some physics that are well beyond BCS theory.
But it's within this approach, it's liquid, but just in a strongly different regime than like the weak.
So you have to be a little bit careful about your definition. So here, of course, there's not a Fermi liquid because it's a superconductor. Okay, so if I suppress superconductivity with a field, you've gone through 2 phase transitions. So it turns out you've, of course, suppressed superconductivity. Also, it turns out that in these materials where they see the quantum oscillations, there's a field-induced charge density wave transition. So you do see quantum oscillations. They're very clearly Fermi liquid-like, but they're across 2 phase boundaries from what I'm looking at. So, that may be essential, or it may be just something that lives in another universe to be treated by other methods. I'm agnostic on that.
But so when you say it's, well, I don't know if you said it, but I thought you said that it's non-Fermi liquid above the dome on the.
So I don't believe,
Question what the-
so what I don't believe is that there is any clean, sensible description of this hierarchy of scales that can be gotten within Fermi liquid theory. Yes.
So you're finding the right number between just number to be closest to the liquid prediction on the underdog regime than in any other heavy fermion, etc.
Yeah. So I don't think Dirk's data is beautiful, but I don't think it's relevant. It's at much higher energy scales than we're interested in here. So, most of his data is on the order of 1/10 of an EV, which is 1,000 Kelvin. So, my colleague, Tom Devereaux, does determinantal quantum Monte Carlo calculations on the Hubbard model. And in the range of temperatures that he can reach, which is maybe down to 500 Kelvin or something, he calculates the optical conductivity, and you see power laws that look just like Dirk's. But I can promise you that all correlations are incredibly short range. It's just some mess due to strong correlations. It's not something that has interesting scaling description or something. So again, the Hubbard model is not the cuprates, but I'm comparing a highly correlated system on which good experiments exist, in this case, numerical experiments, where I see all of these sorts of behaviors without it being associated with anything special. So that's just a warning. It doesn't mean that's the right answer, but it's just, one shouldn't, at any rate, the scales I'm interested in are lower than this. Yeah.
So there must be a caveat to your statement when you say, this hierarchy of scale, the T delta, T theta, it's with repulsive interactions. Like if you have some effective attractive interaction, that's very easy.
It isn't. It isn't. So, okay, so Leo says, what about BEC? Right? That's what you were asking. Okay, there aren't the right parameters. So let's discuss this. So that was my next topic anyway, but this was, let's see, when am I supposed to end? What? 20 minutes, good. 20 minutes is what we need to put BEC to bed. So what's the idea here? So think, for instance, of the negative U Hubbard model. And think about the phase diagram. And what happens is at small u, you have the vector. Tc rises with an as it T theta is on the order of E Fermi. It's huge. On the other hand, if U is big compared to E Fermi, then you form real space pairs. You have pairs of electrons on a site, and the pairing scale goes through the roof. It goes linearly with U. On the other hand, the pairs can only hop in order T squared over U. So Tc does this, and T theta does that. Okay, so that's great. Now, there's something else that happens here, which is that the chemical potential goes below the band. So first place, this involves having attractive interactions that are bigger than the Fermi energy. That's fine for neutral atoms. That's not fine for electrons with charge. So on microscopic grounds, this doesn't make any sense, but let's put that aside. This crossover, oh, and by the way, this is a good example of a crossover. Here, this normal state should be thought of as the normal state of classical charge 2e particles. And at low temperatures, it becomes these classical charge 2e particles become quantum mechanical and Bose condense. Over here, we have a Fermi liquid and we have a BSS description. These are totally different descriptions of the system, different degrees of freedom. On the other hand, the superconducting phase is one phase. There's no phase transition separating them. So it's a good description, and there's this intermediate regime that's very hard to describe. But one of the things that happens in this is that the chemical potential goes below the band bottom. So technically, what BEC is when you have bound states of pairs of electrons. And so that means the pair of electrons has lower energy than two far separated electrons, which means the bound state energy has to go below the band bottom, and the chemical potential therefore has to go below the band bottom. You can see signatures of how this happens if you look at BCS theory. So in BCS theory, we have a gap equation, which we're going to look at a lot, which looks like minus sum over Q, V of Q, delta of K plus Q over 2E of K plus Q, maybe times tanh of beta E of K plus Q over 2, our gap equation. But there's another equation, self-consistent equation, that's usually neglected because it's not important, which is that the expectation value of density doesn't change. And the density, this is, oh, sorry, I have to say what E of Q is. E of K is equal to the square root of epsilon K minus mu squared plus delta of K squared. And mu is the chemical potential that has to be determined self-consistently, and it's determined from the equation N is equal to 1 over N sum over K, whatever it is, EK minus epsilon K minus mu over 2 EK. At least that's what it is at zero temperature. It's something more complicated at finite temperature. And this is to be studied, to be computed for mu as a function of temperature, holding N fixed. And so this will give us a mu, which is equal to E Fermi, the value it would be in the absence of superconductivity. And then, well, as usual, there might be terms that are of order T squared over EF, but then there are also going to be terms that are of order delta squared over EF. And if we have a band bottom, we turn up the interactions, we can see the chemical potential to start to move down toward the band bottom. It depends on the band. It's got a rho prime of EF in it. Okay? Because, this is of order EF, so as a fraction in usual superconductors, this is of order delta over EF squared, which is Tc over EF squared. So if Tc is 10 Kelvin and E Fermi is 10 to the 5th Kelvin, this is 10 to the minus 8th effect. It's really tiny. Don't worry about it. What about in the cuprates? Well, first, in the cuprates, because they're a D-wave superconductor, the BCS to BEC over a phase transition. If mu is below the band bottom, then this quantity never vanishes. So it doesn't matter that delta vanishes along lines in K space, since this thing is always positive, there are no nodal quasiparticles. So if I just artificially turned up, if I had nodes like this is K space, and I started turning up interaction wave superconductor, these nodes would move together. And then at the BC to BCS crossover, when the chemical potential goes below the band, there would be a Lifshitz transition and you would go to a nodeless superconductor. The cuprates are aggressively nodal, so we certainly know that they're on the BCS side of the crossover. But could we understand some of this as being approaching to the crossover? And the answer is there are extremely strong experimental constraints on this. So it's unusual for things to work out in our favor, but in this case, they do. So the band structure of the cuprates looks like this. There's a nodal point here. There's a state at the Fermi energy. So, or more correctly, at the chemical potential. So by looking at this state, both above and below Tc, as a function of doping or temperature or whatever, I can track the position of the Fermi energy here. And in particular, then, I can look for changes in the chemical potential. Changes in the chemical potential will be the V Fermi times the change in the position of the Fermi momentum. Okay, so that's a gift. This node allows us to track the changes in the chemical potential. There are actually several other gifts. One is that it is precisely along the nodal direction that the quasiparticles are sharpest. So the measure of Kf can be done with great precision on this direction, whereas any Fermi surface, there would be much more uncertain position of Kf. And in the material that we have the best ARPAS spectrum on, which is double layer Bisco, there are two bands, but just as a gift, the bilayer splitting vanishes along the nodal direction. So it is possible, as a function of temperature and doping, to follow the shift in the chemical potential. And the shifts in the chemical potential at the superconducting transition are undetectable, which is to say they're less than 1%. So what I can tell you for sure on firm experimental grounds is that not only are the cuprates on the BCS side of any putative BCS to BEC crossover, they're nowhere near any BEC to BCS crossover. Yeah.
General question. So, observation, even in the underdoped side, the cuprate superconductor is on the BCS side.
Yeah.
Shows that the Fermi surface is somehow relevant. Right? The non-interacting Fermi surface. But it's, you look at the normal state, it's what, in this dope Morton's later, why is the Fermi surface relevant?
Yeah, I don't know. Most of what I'm going to do is to tell you why anything obvious doesn't work here. Okay, that will be most of my discussion of this region. I will give you some reasons to think that a doped spin liquid is got some steps in the right direction, but that's the best I can do. Okay, are there any other questions? Yes.
From this reasoning, we know it is a BSC conductor.
Well, I mean, there certainly are cold atom systems where you can, tune what? So, there are other systems that people claim are in or close to the BEC limit. I'm not a great expert on them. I have a strong prejudice against it. I think that the basic interactions between electrons are repulsive, that you have to trick them into pairing. That requires some very clever collective maneuver. And the one place where I know you can get real space pairs is if you turn up the electron-phonon coupling really strong. And there you have a prescription for making extremely good insulators. Chalcogenide glasses, for instance, have electrons that are very strongly paired. There's a huge gap to spin excitations. They're strongly diamagnetic despite having a large density of states at the Fermi energy. So we know there are lots of low energy paired excitations, but they're also spectacularly good insulators because once they form this bound state, they just can't move. So that's a prejudice, but at least for the cuprates, I think this is a fact. All right, maybe I won't, yeah.
So there are other things that people look at, like logarithmic deviations in specific heat, that make people think that there might be a critical point here. You're uninterested in this? You think it's too complicated?
So first place, I never said there weren't quantum critical points. There are slews of quantum critical points. I'm particularly interested in this superconductor to metal critical point. I'm going to be talking about that a lot. There's probably also some interesting critical point over here. There are evidences of pneumatic phases, and there probably are, under some circumstances, pneumatic critical points. At lunch, we were talking about the high temperature tetragonal to low temperature orthorhombic structural phase transition, which is a sort of pneumatic transition, which has a quantum critical point right in the middle of the superconducting dome in LSO. Okay, so I know there are lots of quantum critical points. The question isn't, are there quantum critical points? The question is there some big, whopping, strong quantum critical point that universally dominates the physics of the cuprate phase across many families, and in particular is responsible for the high temperature superconductivity? And I think that's unlikely.
There's not evidence for that.
So there is some evidence for it, but there's also a lot of evidence against it. And what I am certainly prepared to say is that there's no way in the world that such a critical point exists of the type that Sentil dismissed as being sort of ordinary, involving some order parameter. Yeah. Could there be some more exotic quantum critical point that underlies it? That's much harder to rule out. So that means maybe. On the other hand, as I'll also discuss if you ask me about it later, also very hard to rule in. Okay, well, this is a good time to stop. I will go on with a little more about what fails over here, and then I will talk about the rest of the lectures will be talking about what we expect. So I'm going to begin with the proposition that the ideal system on the overdoped side is a Fermi liquid BCS superconductor, and try to understand, which is something we understand a lot about. I'm going to graft in the effects of disorder and try to understand how you can get some of the observed phenomena as a consequence of alloy disorder. Yeah. Right. Yeah.
Argue again why it couldn't be on
Yeah.
the-
So Leo is correct that a way of getting a superconducting state in which the gap is big compared to Tc, and Tc is determined by the superfluid stiffness, is to be on the BEC side of the BEC to BCS crossover. So that is a possible way of getting this hierarchy of scales. However, I presented I first presented a deep personal prejudice that this is never the case for electrons. But more seriously, I presented, I think, irrefutable experimental evidence that this is irrelevant in the cuprates.
For stat sheet.